Hey, everybody. So this is personally the best research paper that I've seen come out in a while now, and it's called, most interesting to me, it's called Retrieval-Augmented Generation as Noisy and Context Learning, a Unified Theory and Risk Bounds. And it's put out by University of Wisconsin-Madison, Salesforce AI Research, and the University of Hong Kong. Essentially, when it comes to rag tuning, everyone has an opinion on it. Everyone has opinions on it. Is it like the best thing since sliced bread? Is it doesn't work very well? Has problems overall, etc. Right? Everyone falls somewhere onto that camp. Like personally, like I think that like fine tuning like via LoRA methods is just far better than rag methods simply because of the fact that it actually adjusts the weights. And then that's my argument within that. But within that, there's no, and within these arguments, there hasn't been like a grounded theory or theorem, right, as to like why exactly it matters in those contexts. And then so that's what this particular research paper lays out, that there's actual theory with regards towards rag tuning. And there's things that we can dissect and understand and know about it. And the bottom line is that it has limitations, right? The limitations that they find, it's interesting to me. So if you know about LoRa tuning, like LoRa fine tuning, like there's a interesting relationship there with like rag tuning. They don't highlight that specifically in this paper, but to me it works the same way with LoRa rag tuning or with LoRa fine tuning. There's you would think that more is better, right? Giving the model more data is better, but there's actually a sweet spot between like usually between like 1,500 to 2,500 rows or so of data. Within rag tuning, it's the same thing. And then what they have found throughout this particular research paper is that it operates off of noise. And then so essentially what is happening is the research paper is like all math. There's like just like basically all math, no very little charts. This is like the only charts that are in the paper here, and then like the rest is like the appendix is all math too. And then like here's the appendix just with like all of their formulas and more of the formulas. But the gist of this overall is very simplistically that it's related to noise when it comes to rag tuning. And then so essentially, and there's two levers that you can pull when it comes to rag tuning overall. And then so when it comes to noise, what that means is that so you feed the models and then they retrieve data, right? And then depending on, let's say you are doing a history query, and then you query what is something about the Revolutionary War, right? And then the model has essentially a upper limit as to the amount of useful information that it will have within that, and it will be able to find within that via rag tuning. So you give it a bunch of examples and information and history, and then some of that data becomes like less good, noisier than other data, right? And then so like that noisier, that less good data accumulates and it accumulates, and then so essentially it just stacks up, and then it ends up being that you get enough of that and it ends up becoming detrimental. And then so you can have you 100% can have too much data when it comes to rag tuning, and that will 100% impact model performance, is what they showcase within here, that you want to stay within that sweet spot. And then there's two levers that it comes to within these models, variance and initial bias. And then what like the trade-off within this and what they find within this, that they kind of, I'll get to this in a second with the irreducible laws of rag tuning and dive deeper into it, is that the rag tuning adjusts variance, but at the cost of increasing bias. And then that's the lever pull, right? So rag tuning can never decrease bias, initial bias within the model. It will only increase initial bias, meaning that like, so essentially like the model has initial biases based off of its training data and its data sets. And then so you give it a query, and then it's going to have, let's say, a confidence score and a bias score. you can increase the model's confidence score. So you can make it more confident and like less like predictive with regards towards something, but you can't make it less like biased inside, right? So if it has, it's going to lean this way. The data set tells it that like X over Y, it's going to be amplified via RAG tuning within those methods, within that bias, right? And then so it's, yes, you can increase variance or decrease variance, which means increasing like the confidence, but you also increase the amount of internal bias within the model. And then so within that, dissecting and distilling all of the math that they put within this research paper, I think this is a better way to break it down into the irreducible laws of RAG tuning. And then so one is that the law of diminishing and reversing returns for quantity. Adding more retrieved examples or passages isn't always better and can even hurt performance. The paper shows that while initial additions can reduce variance-induced error, an intrinsic ceiling on generalization error exists, and excessive less relevant items increase noise, leading to a performance plateau or degradation. So the tuning implication here is that there's an optimal number of retrieved items, just like there is within fine tuning, like via LoRA methods, and exceeding it can be counterproductive. This optimal N doesn't necessarily scale with the number of in-context learning examples. 2, the law of retrieval relevance or quality contamination. The further away or less relevant retrieved items are from the query, the more likely they are to be noisy or misleading, potentially increasing both bias and variance in the error. So the tuning implication here is that prioritize retrieval quality. As retrieval distance increases, noise can increase, and under certain non-uniform noise conditions, like distance proportional noise with rapidly growing distance variance, this can even lead to error divergence. 3, the law of source-specific saturation and noise profiles. Different sources of retrieved data, for example, RAG examples from training data versus RAG passages from external corpora, have distinct noise characteristics and saturation points. So training examples may offer highly relevant signals initially, leading to sharp improvements, but then they can quickly become noisy and harmful as less relevant examples are added, shifting from a uniform to a non-uniform noise regime. What this means with regards towards external passages, like Wikipedia might provide a broader, noisier, but still relevant pool, leading to slower but more monotonic performance increases, resembling a uniform noise regime. Tuning implication of this: tailor the number of retrieved items based on the source. Highly curated but limited sources, like training examples, may have a lower optimal number based before performance degrades compared to vast, more diverse external corpora. The law of bias plateau, and this is what I delved into before, right? So while RAG can effectively reduce variance-induced error, it often is ineffective at reducing the bias-induced error. This contributes to the performance ceiling. So the tuning application of this is that understand that RAG primarily helps with providing relevant context, reducing variance, but may not overcome fundamental biases in the model or task representation learned during pre-training. And then just taking a harsher language within that, they provide the direct correlation. Like it doesn't increase or decrease bias, it can only increase, right? It's a direct trade-off. That the trade-off that you're getting for reducing variance is 100% increasing bias, like it's going to happen. 5, the law of balanced augmentation for multiple sources. When using a mix of RAG data types, the ratio between them is critical, and the optimal performance is not necessarily a monotonic function of this ratio. So the tuning implication of this is that experiment with the mix of different RAG data sources. Performance can improve with an increased ratio of one type up to a point, after which the introduction of lower quality items from that source can dominate and then start to degrade performance. These laws highlight that rag tuning is a balancing act, weighing the benefits of additional context against the risk of introducing noise and hitting performance ceilings. Paper provides a theoretical framework to understand these trade-offs, particularly by modeling rag as a form of noisy in-context learning. And within the paper, they go through like what they want to do within future releases and kind of the limitations of this paper. The limitations are that they didn't use like the very current generation models, which are utilizing like reasoning and test time. Like reasoning and all of that, like none of that is factored into this. So how this performs with regards towards like test time tuning, things like that, is undetermined. Like they don't know, and they don't make any sort of claims around that. So it'd be interesting to see a follow-up research paper around this. But this is the very first research paper that I've seen that grounds all these things in theory, right? Like I said before, like my response has always been with regards towards rag tuning that it doesn't update the weights overall, so there's not as much like benefit to rag tuning. But here you get the actual correlation and an example of what that means. Like it introduces a hard ceiling by not updating the weights, because there's no way that you can decrease the bias in the model, only increase it, as they outline here. And then that increase in bias is your trade-off for this particular method. So there is a trade-off for rag tuning overall. It's demonstrated by the irreducible laws of rag tuning. I'll leave a link to both this research paper as well as this document here if you want to have it distilled down here for you. So here you go, access to both of them. And if you like this type of content overall, please like and subscribe. Thank you very much.